Okay, so let's look at question 1. This question considers cooling a gas in a sealed container until it forms a solid. The diagram below shows the states of matter at different stages of the cooling process. So here we've got it's cooling. I know, just looking at this, I can remember that they are particles. I know this is a gas, this is a liquid, and over here we have a solid. Okay, so it's getting colder, it's turning from gas into liquid into solid. Okay, compare, so it's a compare question. The particle models, so compare the particle models for solids, liquids and gases, and it's worth 6 marks. Okay, so I've got to compare the models for this, this and this for 6 marks. So first thing I do before I even start worrying about the question is I need to give my brain time to think about what the answers may be. So I'm going to do that. I'm going to put my bullets 1, 2, 3, 4, 5, 6. I always like to leave at least one line between each bullet. Sometimes a bullet might only take one line, sometimes it might take more and I have to squish everything down. But what I've done now is I've bought myself time. My brain started to think of 6 differences between these diagrams. So let's have a look. I need to look at differences between what I see. So, okay, so what do I know? Well, I can see that the particles in gas are and liquid are randomly spaced. So I'm looking at how the patterns are randomly arranged. There's a random pattern, whereas there's a regular pattern in the solid. Now I've deliberately done my solid here in a slightly unusual way. Usually students draw solid like that. I've deliberately put it slightly different. Okay, here into this arrangement. That's still a solid. It's a regular pattern. I can guess where the next one's going to be. If I was to add more to this diagram, they would be down here. So as soon as I can do that, then I know it's a regular pattern. Just be careful here when you're drawing states of matter for liquid. The liquid look is randomly arranged, but the particles are still touching. There are some tiny little gaps, but they're still touching. Often we see students drawing a liquid more like a gas with all the particles separated from each other. Okay, so what else can I see? I've said the pattern, random, regular. Well, the distance between them. What about the distance between them? I could say that particles in gas are far apart. Now this is something we often see students doing in a compare question. That's correct, but they'll get no marks for it. Why? Because there's no comparison. Just remember that every single line, every single sentence has to make some kind of comparison. It's a compare question. Particles in gas are far apart. In solids and liquids, they are close together. Okay, what else can we say? Well, what else do we know about the particles here? Which ones are moving? How are they moving? Which one's moving fast? Which one's moving slow? Okay, so sometimes you'll see these diagrams with little lines like that, indicating that these particles are moving very, very fast. They're racing around all over the place. Okay, I haven't got it in this, but hopefully you can remember that these particles are moving very fast. They have a high internal energy store. They've got a lot of internal thermal energy store is very high. So I could write particles in gas move fastest. Have I compared there? Absolutely. Because fast est, I know that they are faster. There's no point me writing they are slower in solids and gases, solids and liquids, because particles and gas are fast est is a comparative word. If I just wrote particles in a gas move fast, that's not enough. Okay, but fastest is fine. I can actually expand that out there. Particles in solid. So I can keep using that same point about speed, move slow est. Or I could say they have lowest kinetic energy store. Okay, those two things I've said there are the same point really, because they've got the same mass. The only difference is the speed. The idea is they do move the slowest, so I wouldn't necessarily need that extra sentence there. But if you wanted to talk about kinetic energy store, that's absolutely fine as well. What else? Let's look back to the diagram. We can see here the container they're in. This one fills the container. These two don't. That's a comparison, so let's use that. So particles in gas fill their container. So fill the container. Is that a comparison? No, it's not, because I've not said anything about the other particles, the other states of matter. So solid and liquids do not. Okay, what other comparison can I make? Well, it gets more difficult the more comparisons you have to make. Obviously, the get the full marks is a tricky one. So we're looking here. This one fills the container. Liquids actually take the shape of the bottom of the container, which is something that neither of the other ones do, and solids hold their shape, don't they? So I could either say solids keep their shape, or here I haven't mentioned at all the fact that liquids take the shape of the bottom of their container. So let's add that for the last mark. So particles in liquid take shape of bottom of container, which again I haven't yet made a comparison, so they do not in gases and solids. So sometimes it's as simple as saying they do not do something in gas and solids. Other things, if I was really struggling there, so I'm going to add, I'll add some more bullets just in case. You may have said that particles in the solid, liquid and gas, if you just look at them, what have they all got in common? Well, the particles don't change size. The particles themselves don't change size, which is a really common misconception. Sometimes students say that the particles in a gas are smaller than in a solid, which they're not. Okay, so there's a comparison there. You're saying something they've all got in common. The same number of particles in each diagram, which again is a very common misconception. Textbooks often do this, where they have, here we've got 9 particles in the solid. Quite often they'll only draw 3 in the gas, which is really wrong. The number of particles is the same in each state of matter. So you can also put similarities here. Particles in solid, liquid and gas stay same size. And you could also say same quantity or same number of particles. That's right. So same quantity of particles in each state of matter. The particles don't disappear and you don't make new particles. One other thing we could add here, actually coming back, just thinking about it, is we could also add that the forces between the particles, so the forces, the reason that there are these huge spaces between our gas particles compared to our particles in a solid is because the forces of attraction between them are much, much lower here and much, much stronger here, and they're kind of in between for a liquid. So, so forces between particles are strongest in solid. Gases have no, or almost no, so let's change that, very weak forces of attraction between particles, and that's why they can spread out. So forces between particles are strongest in a solid. The fact that I wrote strongest there, that sentence on its own at the beginning would be enough to get the marks for that. That's another comparison you could make between the particle model for solids, liquids and gases. Okay, I hope that's useful.